Hello, good day. How are you? Welcome to Yebo Tutor. And we are back and we are discussing some of the key points that we went through last week. So just want to make sure that we iron out some questions that we also received so that we can see how to crack this topic. So my first question to you is, did we finish up the questions that we had? Did we finish up the questions that we had? So as a quick review, we are just going to look at each and every step that we walked through. There was a discussion on that. Okay, so let's get to see what questions we had last time. We said we are working on chemical equilibrium and we did some calculations based on this topic. And then our paper, which we were focusing on, is the 2021 paper, the 2021 paper. So we can now look at some interesting points, some similarities in some of these questions. This will assist you to be smart about your exam or your papers, isn't it? So let's get to see something that's very interesting here. So this is the 2021 paper. And this is our question. It's question number 6. As you can see, question number 6 for chemical equilibrium. And their first question is what? Their first question is define the term. Define the term chemical equilibrium. And so, as you are putting your finger on that paper, let's just scroll to this other paper that we have on the screen. This is grade 12 once again, but this is the 2020 paper, right? So this is the 2020 paper. So I just want you to see something very interesting here. So we've got our given equation, right? And we've got our very first question, which has to do with the definition of chemical equilibrium. It's like an introduction into the topic. So let me just scroll down and see if we will be able to see this paper well. We want question number 6, right? Question number 6 focuses on chemical equilibrium. Question number 6, there we go. So this is your question number 6 for the 2020 paper. So this is what you can see here. This is for the November 2020 paper. So look at the first question. So it has to do with the dissociation of iodine molecules to iodine atoms, right? I is a reversible reaction taking place in a sealed container at 727 degrees Celsius. The balanced equation for the reaction is given, right? Kc for the reaction is 3.76 10 to the minus 3, right? So look at what we have as their first question. Their first question, write down the meaning of the term reversible reaction. Look at that. Write down the meaning of. So you are basically giving a definition. So can you see something that you need to be aware of for most of your papers or for most of our papers? It's crucial that you do not only focus on just the calculations and the multiplication and the Rice diagrams and all those problem solving. You also need to remember and to recall and to master the way to define your terms. So let me ask you now. In our 2020 paper, we were defining the term chemical equilibrium, right? So now you are in this new paper. Let me just scroll here and say this is now the 2020 question 1 of the 2020 paper. So actually question 6 and then 6.1 is where we want to what? To write down the meaning of the term reversible reaction. The term reversible reaction. So what is the meaning of the term reversible reaction? When we say it is reversible, what does it mean? Let's hear from you. What does it mean when we say this is a reversible reaction? What does it mean? have written the meaning now, what are some of the synonyms that you can use for reversible? When we say synonyms, what are some of the words, scientific terms that you can use to define or to write the meaning of this term, reversible reaction? If it's reversible, it means the reactants form the products, and simultaneously the products dissociate into the reactants, isn't it? Or the chemical reaction is bidirectional. It can take place in the conventional reactant to product direction and the reverse. Right. So it is reversible. It can take place from the products to the reactants. Right. So you've got a lot of options there for your definitions. So this is one similarity that we've seen, right? We've seen the definition being a very important part of this topic. So this means all your terms that are within this topic, obviously, and other topics, you need to remember the descriptive, right? The words do not compromise the exact definition of the term, right? And let's say exact, right? Okay, so I think that part is looking good. That was question 6.1 in the 2020 paper, which we have seen to be almost the same as the 2021 paper, question 6.1 as well. Right, so let's get to see something here. In the 2020 paper that we worked on, so I'll just scroll to it, we said they provide this chemical reaction, right? In the 2020 paper, they provided a chemical reaction which is a hypothetical chemical reaction. In the 2020 paper, they have a known chemical reaction using some species that we already know, which is iodine only in this case. So can you see what's happening here? There is always some chemical reaction that is being provided. Can we check if the chemical reaction is balanced? Please tell us, is the chemical reaction that you see here balanced? Is it balanced? This one is a simple chemical reaction, just because it is one type of species that are participating. So we have iodine, and we have how many of these iodine atoms? 2 on the left hand side, and how many of these? We have 2 on the right hand side. So our chemical reaction is what? Is balanced. So that's always the first thing to check, because these coefficients, they affect your calculation of the chemical equilibrium constant. Now, next thing, look, they gave us a chemical equilibrium constant. They say Kc for the chemical reaction is 3.76 10 to the minus 3. Now my question is, what is the meaning of that? Are the reactants more than the products? What is the meaning of this number? Are the reactants more than the products? Right, so consider Kc of the chemical reaction, right? Please give me the formula for Kc. What divided by what? And this is equal to, according to this question, 3.76 10 to the minus 3. 3.76 10 to the minus 3. Right, that is our Kc. So my question to you is the following. If our Kc is like this, right? If our Kc is like this, which chemical reaction, which path is most likely to take place? Yes. Which process is most likely to take place? The forward process or the reverse process? Right. So let's just see. This Kc is a ratio. What did we say the Kc ratio is? So I want you to write down the chemical equilibrium constant, the expression or the ratio for the iodine reaction that is on the screen. So write down the Kc equation, right? Kc equation for the iodine reaction shown. You tell us, what is the Kc chemical equation for this iodine that we see here? Right, so let's do it. Right, so have you done it? Does it make sense to you? Have you figured this out? Have you figured out what to put in that chemical equilibrium constant calculation equation? Okay, what did we say? We said on the numerator, look at what we did last time, right? Look at what we did last time. So we have this chemical equilibrium constant calculation. It is based on this chemical reaction. So I'll just, it's 2P plus Q2 is equal to 2PQ. So we wrote our Kc as follows. Our Kc was equal to, we look at the products, isn't it? We look at the products and we look at all our species that are neither solid nor liquid. So we have PQ as a product and it's raised to the power of 2. We have P as a product, as a reactant, is raised to the power of 2. And we have Q2 as a reactant. Did you see that? So next is the same thing for this particular case. For this particular case, for the iodine reaction. For the iodine reaction. So what do we put in the numerator? In the numerator, we have the products. So we've got the products, and that is what? That is just the iodine gas. So this is the monoatomic gas. And it is raised to the power of 2. In the denominator, we have the reactants, and we have the iodine molecule. So this is our expression of the chemical equilibrium constant. Now, let's compare something. Remember I said, what is the implication of this number? This number is now less than 1, isn't it? It's now a very small number. It's now less than 1. So if it is less than 1, what does it mean? If you have a fraction and that fraction is less than 1, what does it mean? It means you should have more, the concentration of the iodine gas, the molecule, is actually higher than the concentration of the monatomic iodine. Right, so this is in contrast to last time. Can you see what happened last time? We had an equilibrium constant that is greater than 1, right? We had an equilibrium constant that is greater than 1, which was found when we noticed that, okay, our concentration of the products is actually much higher than the concentrations of the reactants. That is what we observed last time. So this question is actually like the reverse. Do you see that? It's like the reverse in terms of the chemical equilibrium constant Kc. Right. So our Kc is 3 times 10 to the power of what? Of minus 3. This means we've got a higher concentration of these what? Of these reactants. So this means that this chemical reaction is actually it is actually favored if it is the reverse reaction, right? The reverse reaction is actually favored in this process because there's more of what is on the left hand side. So it's actually possible, and it's good that we've seen an example like this one. Okay, so these are some of the similarities, right? And these are some of the things that you can actually take advantage of as you practice, because these questions, they will change here and there, but they will not be completely out of what you have been seeing before. Okay, so that is what we've seen. We've seen that the question required us to find the meaning of the term reversible reaction and so forth. So, right, just to take our attention a little bit away from this question, I just want us to finish off the questions that we had in our paper. I hope we'll be able to do that very quickly. So you remember last time we went through these calculations. We've seen the first part, we've already seen it. We've seen the similarities. We remember calculating this, and we also remember identifying or arguing using Le Chatelier's principle. And then calculating the equilibrium constant, we also did that, right? And then we used the Rice diagram, and then we came up with some moles. And then now, how will the equilibrium constant, okay, we answered this one. So we had two questions, right? We had two questions. The question 6.3.1 and 6.3.2 are the last two that we did not do, and I gave you some homework. So I'd like to find out, did you do it? And if you did it, please, let's share our answers and discuss. Tell us what you got as you answered this question. Okay, so what were your solutions? What were your solutions? This question said, more Q2 gas is now added to the reaction mixture at constant temperature. How will each of the following be affected? Choose from increases, decreases, or remains the same. Choose from increases, decreases, or remains the same. The first one is the yield of PQ. So PQ is our product, isn't it? PQ is our product. So what happens to the yield of PQ? Does it increase, decrease, or stay the same? And what is your reasoning? What is your reasoning? Right, so let's just see what happened. This is a process that is taking place at constant temperature. What have they done? They have added more Q2 at constant temperature. So constant temperature is telling us about what happens to our chemical reaction. Do you remember that we said our chemical reaction is what? Is endothermic, isn't it? Is that so? Let me just revise it. Was it endothermic? Okay, it is actually exothermic. So the reverse was the one which was endothermic. So we figured that it was exothermic. Okay, so we said that the process is exothermic. If we maintain our temperature constant, then we are not going to affect our chemical reaction, right? Then, when we raised the temperature last time, then we favored the reverse chemical reaction. Now, if we add more of this Q2, if we add more of the Q2 at constant temperature, what will happen to the yield of PQ? What will happen to the yield of PQ? If we add more of the Q2, what will happen to the yield or the output of PQ? What do you get? What happens? What happens? Yes, tell us what happens. Right, so your PQ in this case, by adding more of the reactants, it's obvious you're increasing the yield, isn't it? You're just adding more species, right? The reaction will take itself to equilibrium. This is a dual process. So this chemical reaction occurs in the forward and the reverse, right? So when you increase a certain amount of the species, then you will take it off equilibrium, but it will get to equilibrium since in this case we are at a constant temperature. So the effect of the increase, so this one is an increase. So the increase in your product, we have increased Q2. What happens to the moles of P? What happens to the moles of P? When you increase that Q2, then your number of moles of P are going to decrease, isn't it? Your number of moles of P are going to decrease. So you can tell that from our rice diagram. So this basically covers that question that we had last week. It covers it to the end. But when we started there, we just see some interesting spots, some interesting things where you see that these questions have a lot of similarities. Let's just scroll through this question, this 2020 question, and also see an additional few things that are similar to what we worked out last time. Right, so 6.2. At equilibrium, the pressure of the system is increased by decreasing the volume of the container at constant temperature. How will each of the following be affected? Excuse me. Okay, so this is an interesting one. So you're choosing from increases, decreases, or remains the same as usual. So you want to find how the value of the equilibrium constant is affected, right? How the value of the equilibrium constant is affected, and how the number of iodine molecules are affected if you change the pressure. So can you see the concept of changing parameters? This is obviously Le Chatelier's principle that is supposed to apply here. So when you change the experimental parameters, Le Chatelier's principle states that equilibrium shifts in the direction that should cancel that change in parameters. So in other words, if you increase the temperature, the chemical reaction that makes use of heat is the chemical reaction that is favored, right? So when it is favored, then that increment in heat is cancelled out because the heat is actually used up in the endothermic reaction. So this is the same, right? This is the same. Now we have a pressure system here. So we have a gas. So it's important for you to now start thinking like a chemist and a physicist, right? So you've got a gas in a what? In a sealed container. Did they say sealed? Let's just see that. Yes, sealed container, right? Sealed container, and the sealed container is at 727 degrees Celsius. Okay, good. So it's in a sealed container, and then the pressure of the system is increased by decreasing the volume of the container, constant temperature. So pressure is increased by decreasing the volume. So let's draw the container. This is now 6.2. 6.2. So this is our container V1. This is our container with volume V1. Then this is our container with volume V2. This is our container with some pressure P. And then this is the container with higher pressure. P1 is greater than P. Let's just say P naught. P1 is greater than P naught. Right. So how will each of the following be affected, right? So yeah, the temperature is the same. You're not changing the temperature of this process. So first of all, the chemical equilibrium constant. So we already said Kc is equal to, this is just the concentration of what? Monoatomic iodine squared over diatomic iodine, and that's our chemical equilibrium constant. And we said it's actually 3 point something 10 to the power of minus 3, 76 10 to the power of minus 3. That's the original chemical equilibrium constant. Right, 3.73 10 to the minus 3. So what will happen? The question is, what will happen to this chemical equilibrium constant when you have reduced the volume? You have reduced the volume. Let's just draw some molecules here. Let's just draw some molecules. Let's say, where is the chemical reaction? It's right. So we have our diatomic iodine, right? So let's just say diatomic iodine. Then we also have some monoatomic iodine. Monoatomic iodine. So for every 2 we have those. Right. So this is monoatomic iodine. This is our diatomic iodine. Right? If we do not do anything to this container to break it apart in order for us to increase or to put a chance of some gases escaping, but we just reduce the volume. So we have just compressed it, right? Volume reduction. I think you've seen us trying it out. So we've just reduced the volume. So you don't really change anything as far as the contents are concerned, isn't it? Let's just see that. Let's just see that. Right. Give me a moment. Right. So what are we looking for? Right. We just want, let me just see. Right. Let me just see if we have the right program here. So we want this container of ours. Yes, we want this container of ours. We want this container. Yes, it's coming up. It's coming up. Give it a moment. Give it a moment. It's coming up. Coming up. Right, did you see something here? Look at the screen, right? Look at the screen. So I just want to restart what I'm doing here. So what we have is just a container, and I've got some way of controlling it. Maybe let me share this once again with you. You may have seen this before, but in case you're coming in only now and then you see this. So try this simulation. So you can pump a gas in, and change the volume, right? Change the volume. So we are going to reduce the volume, right? I'll put the link there. There we go. So it is courtesy of the University of Colorado. They are doing some very wonderful work for us to learn. Okay, so what we are saying is this. This is the process, right? This is the process. They simply said this is a sealed container. So to demonstrate sealing, I think when I was opening this, you saw that the gas particles escaped, right? So if I could maybe pump just a little bit, yeah, just those. So can you see, if we have a container that is not sealed, then it means our gas particles will escape. So there's a gas particle. This one is likely to escape, isn't it? Look at that. Straight line out, okay? This one won't escape unless it's reflected, and then, okay, it missed. But it will escape. So let's wait for it to escape, right? So it will escape. It will hit this wall. Obviously, it has to be reflected to somewhere there. Then it is reflected again. Then it will escape. Yeah. So it will escape. So this is what we are seeing. This is what we're seeing. This is our container, right? This is our container. And these are gas particles, right? So unfortunately, okay, yes, there we go. So it's escaping now. So these particles can only leave this. What? This particle is not escaping. What a bad demonstration. Okay, what I'm just trying to say is, in the question, they did not say that this container was changed. So it is still a sealed container. If it is still a sealed container, this means this container will not have any changes to it. So the particles that we saw here, so I've got two pairs, they will still be in there. Then, finally it is escaped. So that's an unsealed container. And then now, when we shut this, that becomes a sealed container. When it is a sealed container, no matter how much we reduce the volume, there is no, the particles that are in there will still be there, right? So I'll just pump this a bit with some particles, and then I'll change and put some particles that have a different color so that we can say, okay, we have these particles, the iodine particles, which are the purple ones per se in this case, and then the smaller ones, the red ones, are the, let's say this is just diatomic, but they are separate. So no matter how much, look at our pressure right now, look at our pressure. Our pressure is, let's say 2 atmospheres. It's just fluctuating, right? So let's say it's about 1.5 atmospheres. It's fluctuating up to 2 and then up to 1.2, yes, yeah. So approximately 1.5 atmospheres, that is the pressure in the system. You can also change it to kilopascals, since we use SI units. So now I will reduce the volume. When you reduce the volume, you will certainly increase the pressure. So it's now in the order of 300 kilopascals, right? If I go back to the atmospheres, that time it was around 1.5. Now it's at 3 atmospheres. So the pressure does increase. So it is true that this pressure does increase. But the question is, has there been a change in the concentration of these species? So I'll just copy this and paste it in here, right? Paste another in there to represent these 2 pairs. And then we've got these ones. We can copy that. And we also paste it in there, right? So you can see that we have our first, our second, our third, and then our 4th monoatomic iodine. There we go. So the concentrations of these species have not changed. Can you see that? The species are still in there. The only problem that has occurred is that these species have now been put into a smaller volume. That's all. That's all. So the pressure rises. So in this case then, according to our question, we wanted to just find out what happens to the equilibrium constant, right? The value of the equilibrium constant, what happens to the value of the equilibrium constant when you have reduced the volume and thereby increased the pressure. So the value of the equilibrium constant remains the same. The Kc value remains the same. Why does it remain the same? Okay, so by the way, the answers that have been given for you to select from are increases, decreases, or remains the same. That's it. You don't need to explain. They just stated and said how will each of the following be affected. That's all. So you don't need to explain in 6.2.1 and 6.2.2. Okay, so then what happens to the number of I2 molecules? What happens to the number of I2 molecules? What happens to the iodine, number of iodine molecules? Right, so the second part, iodine molecules, the number of I2 molecules. Molecules. So these molecules, what happens to them? So look at our equilibrium process. Look at our equilibrium process. We've already seen where is the equilibrium equation. Okay, so maybe let's just scroll up on the question. Right, while you're figuring it out, let me just scroll up. There we go. So this is our chemical reaction. This is our gas, diatomic gas, and it changes to monatomic gas. But this process of forming the diatomic gas is more likely to take place, right? It's more likely to take place. Okay, so now we've just increased the pressure of this system. But how did we increase the pressure? By reducing the volume, isn't it? We've reduced the occupied volume. So what should take place now? Let's think Le Chatelier's principle. What should take place? Remember, you're moving in steps, isn't it? So according to Le Chatelier's principle, the process, be it forward or reverse, which favors a counteraction of the change in experimental parameters is what it takes priority, right? The process that counteracts the change in parameters takes priority. So that's the process that should actually be promoted in this chemical reaction when you have reduced the volume. So the first thing is number one, volume was reduced. When volume is reduced according to Le Chatelier's principle, the principle requires us to state that the process that counteracts a reduction in volume is promoted. So the process that increases sorry. So okay, so we have here an increase in pressure. We want something that will decrease the pressure, isn't it? We want something that will decrease the pressure, right? So which means the reaction that is leading to what? To the smaller amount of gas. which has less molecules is the one which must be favored, right? The one which has less molecules, it is the one which has to be favored. So from Le Chatelet's principle, you can tell then that the reverse reaction is actually promoted, because this one is the one which has what? Which has less molecules. Stoichiometrically here, we just have one of the diatomic iodine. So basically the reverse reaction in this case is promoted, right? The reverse reaction here is promoted. Right. So in these questions, these are some of the concepts that you're dealing with. You're just looking at parameters of the experiment, and you're looking at your understanding of Le Chatelet's principle, and you apply it. That was 6.2. Any questions on that? Let's discuss. Let's discuss. Any questions on that? Let's discuss. I think that we have seen the question, and we've seen that the number of I2 molecules must increase. So we need the I2 molecules to increase. I2 molecules must increase. Okay, basically I think that should cover up all that we needed to look at today. If there are still some questions on equilibrium, let's also discuss, and also just indicate that you'd like this question to be worked out, or you want us to move to our next topic. So let's also prepare okay, we may not need to revisit acids and bases, just because we did some questions on acids and bases, and these questions will literally be, circling around the same concepts. So we are likely to work on some electrochemistry from next week, and that should be which question? Let's just see if we have the question number here for the electrochemistry questions. Right, let's just see. Okay, this is number 7, that's acids and bases. Oh yes, so question number 8, right? Question number 8. Okay, so as your homework, please prepare for question number 8. Let's start with the 2021 paper. So please go and work out question number 8, 2021, and then we'll look at the 2020 as a review, just like we did today. Okay, so let's get busy. Wishing you the best this weekend, and I think we've covered sufficient information and practice questions for chemical equilibrium. But again, we're still open. If you'd like to work out another question, maybe you did it at school, or you found it in some paper, or you just want to work it out, or even in a textbook, you can send it through, and then we can discuss it. So all the best with your studies and have a pleasant weekend. Have a good